Hello students, welcome back. Now let's go to the example problem here for the central limit theorem. Example 2.3. What did you do previously, by the way? We talked about what it means by sampling distribution, and then we emphasized sampling distribution of sample means. And we went through some simulated experiments on the sampling distribution of sample means and checked out with these theoretical values. Pay particular attention to this one, sigma over square root of n, the standard error. Oops. And also, we did some visualization. Clearly normal, right? So combine these, the normal, and then also sigma over square root of n, and we end up with this conclusion. So mean stays the same, that's the expected value, but new standard deviation, or which we call standard error, is sigma over square root of n. And that generates these formulae, and especially this one, combined with the picture. Okay, so far so good. But now let's do an exercise problem. And here is an exercise problem. And I wanted to apply the central limit theorem. So I ended up getting a random variable that does not look normal at all by any stretch. Let x be a discrete random variable with this mass function. And as for probability mass function of a discrete random variable, does everybody remember? We went through this in lesson 6. And then we discussed how to find the mean and the standard deviation of discrete random variable. So what we do, we multiply these two, multiply these, multiply the third line, multiply the fourth line, and then add them all up. And that is the expected value. And then the standard deviation, well, yeah, I'm going to show you in a moment. Let's suppose we calculate all that as we did in lesson 6. And with that mean and the standard deviation, and also 100 repetition, we're going to get mu and sigma over square root of n so that we can do normal approximation. And that's how we're going to answer this question. If everything made sense, great. But if you're a normal student, probably it must have been too hard. So let's take a step-by-step approach. Step 1, let's calculate the mean and the standard deviation of this discrete random variable given by this probability mass function. Okay, mu, that's easy. Payoff times the probability, payoff times the probability, payoff times the probability, and so on, add them all up, and this is the expected value. Which means no matter how many repetitions I take, no matter what kind of sampling I do, expected value is 1.3125. Now, how about standard deviation? Well, here's a standard deviation computation. Payoff times, probability times deviation squared, probability times deviation squared, and so on and so forth. You get variance, take the square root, and that's the standard deviation. So, with mean and standard deviation, we can calculate the standard error now, and that's over square root of 100, isn't it? Square root of n. And in this particular case, this is my sigma value over square root of 100. And then calculating this, there you go. This is my standard error. So we want to use the central limit theorem, right? This exercise is about central limit theorem. we need mu and SE. And that normal random variable is going to approximate whatever we want to do. How do you find mu? Well, there you go. That's not too difficult. Now, how do you find out sigma over square root of n? Well, find sigma first, and then divide by square root of n, and there you go. We're going to be using this and that for our normal analysis. Now, how does it work? Well, let's see. Let me put some space here. Okay. I can now see almost the entire problem in the single viewing window. And then let's go to the drawing mode. So we are doing a normal approximation, right? So let's draw a normal picture. And this normal picture will approximate whatever random variable we will be working on. And it is centered at the mean of 1.3125. Okay, and then we want the probability that this random variable given by sampling distribution of sample mean exceeds 1.2. So this is what we want, 1.2. Now, where is 1.2? 1.3125 is here, so 1.2 is gotta be here. 1.2. Can everybody read this here? And then shading is to the right. Because I want x greater than 1.2. So that's what we want. Now, if you do your z-score computation using end minus center over SE, and then look up the z-table, you'll be able to get the left-hand side shading. Get that from the normal table, and what I want is right-hand side, so subtract from 1, and you're going to get what you want. Make sense? Okay, this is a z-score computation now. Can everybody read this? Maybe I should increase the font a little bit further. End minus center over SE. Well, 1.2 minus 1.3125 end minus center over standard deviation over square root of 100. That's a standard error. And if you do it right, you're going to get negative 1.62, approximately speaking. Looking up negative 1.62 from the normal table, getting the probability, which is the left-hand side shading, and getting the right answer, the detail is left to the students. Instead, let me just give you a visualization. This is what we want. Centered at 1.3125, greater than 1.2, so shaded to the right. And then look up the answer key, look up the normal table associated to this z-score. You're going to get left-hand side shading. And what I want is right-hand side shading, so 1 minus of that. In the end, you get this probability. So how deep is this problem? Well, we want normal curve analysis, x greater than 1.2, but in order to do that, we need the z-curve. For z-curve, I need not just x, which is the end, but also mu and SE. Because you see end minus center over SE, so 1.2 end center, which we'll have to calculate from here, and then SE, sigma over square root of n, again you have to calculate from here. After calculating all those, we can apply this z-curve picture and then z-table. So this is a multi-step problem, pretty deep. Now, why did I select this problem? Well, one reason was, of course, the depth. I wanted to review something we did way back in lesson 6, but that's not really the only reason. As I'm showing you here in this visualization, we began with this probability mass function. Now, does it look like a normal random variable by any stretch of imagination? No way. This is discrete. No way close to random variable. I mean, no way close to normal. Now, if you redraw that as a probability histogram, instead of those dots, express those as non-overlapping rectangles of same width, probability histogram, the same thing. And again, that does not look like normal at all. But then again, from here, we apply the sampling distribution of sample means and then repeat it many times to see the behavior. We get something like this, and that looks very much like normal. And then not just any normal, but the normal given by this, the mean and standard error, which is sigma of square root of n. So you get this central limit theorem in action, even for extremely out of ordinary. I mean, it doesn't look like normal at all, but still it works out. That's what I wanted to show you. Coming back to this central limit theorem, it does not matter where I start. No matter how outrageously complicated or outrageously simple this initial random variable is, if I take sufficiently many independent repetition and take the average, then we can approximate that behavior using the normal random variable of same mean mu and the standard error sigma over square root of n. That's the central limit theorem. So how important in terms of theory? Number one, we can do computation. So yeah, that's great. But also, it does not depend upon where you start. No matter what random variable, no matter what circumstance, independent average follows normal. Now, what is the motivation behind studying normal random variable? There were three. Number one, it's simpler. We discussed it in lesson 7. Number two, it was useful. We went through some realistic examples. Number three, right here, central limit theorem. It does not matter where you start. If you take the average independently, that becomes normal, more or less. And by the way, that is why the normal random variable is so useful to begin with. Because you see, in human body or any kind of system, I mentioned human body because the previous example I discussed in lesson 7 was the growth of baby is human body, but doesn't have to be a biological system. In any system, a lot of averaging process is going on everywhere. Every time averaging process is going on in real world situation, in systems of nature or in stock market or whatever, in diversified funds or in human body, everywhere. And whenever we have averages, due to central limit theorem, we are looking at normal. That's why normals are everywhere. So we had some difficult example and we went through some difficult theory, but in the end we got it done. Central limit theorem, normal random variable. Why is it so important? Why is normal everywhere?